All right, so our next session, we're going to be talking about TCPIP and user space. We have Tomek from our team over in Poland, and Ed from Cisco will be up here. Or, there's Ed. Okay, great.
So, hello. My name is Tomasz Zawadzki. I'm cloud software engineer at Intel, working on SPDK. Ed will come up in a second. So this talk will be about VPP and SPDK, meaning why and how did we move the TCP stack used in SPDK to user space. We'll give you a brief overview of the current iSCSI target architecture. Then Ed will talk in detail about FDI project as well as the VPP platform. Then going back to what's been released in 1804 with the integration with VPP, as well as some pointers to get you started using it. And of course, at the end, Q&A session. All right. Solutions like RDMA have made a lot of progress and made a real impact on the industry recently. But you have to keep in mind that TCP/IP transport has been around for much longer and is not going away anytime soon. There are still many use cases where TCP/IP is the best one to use, as well as a lot of deployments already in the field using it, and the change is not going to happen overnight. A proof of that is that TCP/IP is going to be implemented as a transport for NVMe spec. All of that makes the technology very much relevant today. So with the current iSCSI target, this is our architecture, and SPDK has made a lot of effort to alleviate the drawbacks of running storage services in kernel. Although using POSIX sockets within iSCSI target actually partially negates those benefits. The data path for iSCSI is using syscalls all the way up to the driver and then back to SPDK. In addition to that, it adds back the reliance on interrupts through kernel usage. So that's the current state that we had before the 1804 release. So please, Ed, that's your part.
Excellent. So is the mic working? Okay, there we go. Very cool. So, thank you for the clicker. I tend to prefer really interactive talks. So, really quick, calibration of the audience. How many of you can raise your hand? Oh, come on, guys. Okay, I've presented so far this week at the big communication event. I presented 2 weeks ago at KubeCon. They could get to at least 90%. How many of you can raise your hands? All right, there we go. Now, I'll be using this mechanism throughout because I am not actually a storage guy. I'm a networking guy, which is just close enough that I can deceive myself into believing that I understand what the hell you people do. We all know that's false. So I will be asking you questions because it's good for us to understand each other, because I believe, and you can help confirm this for me, that we need each other desperately, right? So really quickly, how many of you have storage things that you do that basically are destined to hit the network? Okay. How many of you have storage things that you do that are never destined to hit the network? Okay, I count that as 0 hands. So I'm on the right track. We do actually need each other. So I am the technical steering committee chair at an open source project called Fido. It's the fast data plane, FDIO. We pronounce it Fido because it's cutesy and we have a dog on our logo. And effectively, what Fido is doing is it's giving you an extremely fast data plane purely in user space. Now, it's worth understanding how this differs from DPDK, because the DPDK project does some amazing things that we take advantage of. What we do is somewhat different. And we find the easiest way to explain it is to talk about this in layers, where we talk about network I/O as how do I get a packet from a NIC or a VNIC to a thread on a core so I can do something interesting with it. It turns out that it's fiendishly complex to do that well, and DPDK does it brilliantly. But once that packet has gotten up to a point where you need to process it, where you need to do the standard things involved with routing and switching, with the incredible richness of features that people are used to in the network, that's what we tend to focus on. So one of the key projects in Fido is the vector packet processing project. This lives at the packet processing layer. It is extremely high performance. As I said, it's pure user space. It runs on Intel, ARM, and PowerPC. And it is a software base that we've actually shipped before we open sourced it on both embedded and server products since about 2004. So it's an extremely battle-tested, extremely industrial-grade technology that we open sourced about 2 years ago. So how does it work? Some of the magical things that makes VPP so fast and efficient are that it basically, number one, decomposes all the packet processing behaviors into a directed graph. Not necessarily an acyclic graph, although it's not a good idea to circulate forever, but into a directed graph. And then we take the packets that are coming into the system, and we take a whole vector of those packets at a time. And we go node by node, and I've got some subsequent slides that show this, so that we only take the iCache hit for a node for the first packet in the vector. After that, we don't, and there are a bunch of other tricks that this vectorization strategy allows us to do in the course of processing packets quickly. So we get a lot of optimization around instruction cache and data cache usage by virtue of doing this. So really quickly, as I'm going through these next couple of slides, feel free to stop and interrupt if you have a question. Because if you have a question, someone else in the audience has a question, and it's better to get the confusion out of the way immediately. Everybody with me? Awesome. Yes, you have a question. There we go. Cool. So this is, again, packet processing graph. So you've got the graph. You have a bunch of graph nodes. They do things. That particular graph node handles ARP. Most people are familiar with ARP. You've got input nodes. These are where packets come from, or rather, where vectors of packets come from. And they can come from all kinds of things. We have a DPDK input node we're very fond of. It's what you do if you really care and you're using hardware. But we have other things like vhost user, AF packet. We've got tons of ways into the system. Then you get a vector of packets. It's some number of packets. It's an n value, typically less than 255, because we do bound it. And effectively, every time we run through the loop, we go back to DPDK and we see how many packets it has available, and we take them all. So we don't rate limit them, we don't do anything fancy. It turns out that complicated is expensive, and so it's slow. So that vector of packets comes in, and the whole vector runs node by node through VPP. This does a number of things. One is it means your first packet warms up the iCache. But it also means there's a ton of stuff you can do where you can amateurize a bunch of expenses across the entire vector. The iCache hit is one of them. There's also a bunch of things you can do about prefetching packets. We play all kinds of games abusing the pipeline. We even play a lot of games abusing parallelization of instructions. So that's where a lot of the magic takes place. So really quickly, how many people are wondering what happens if you have a vector that doesn't go through a single path in the graph? That's exactly the thing you should be wondering. The answer is that effectively the vector gets split at some point if you have different paths in the graph, and you end up cycling through that. We have a little bit of magic we do in there to maintain packet order, but it ends up working out. It's a little bit slower if you get a heterogeneous vector that comes through, but this is where we win at statistics. Because remember, I told you there's a bunch of fixed costs that we're amateurizing across the entire n of the vector size. So if we take a little bit longer because an ARP packet fell in here, then when we get back around the loop to the beginning to get packets, we have a few more packets. So the average cost of processing a packet declines, and we tend to catch up. And it happens to be that the way network traffic works in the real world, the statistics end up winning out in our favor. Yes, please. Mics. We have to get mics around. Also time, but mics, yes.
Yeah, so let's say 256 packets. I don't know what size.
255 is the max vector size. We almost never hit that.
Wouldn't your data cache get churned before your iCache gets churned?
So effectively, what we end up doing is that as we're going through and processing these packets, we'll process some number n at a time in our loop. There's a little bit of loop interleaving. And so while we're processing the first few packets in the vector, say the first two if you're dual looping, you're doing the prefetch for the next set. So that by the time you come around to them, you've already actually pulled them into the data cache as well. So we don't pull the whole vector into the data cache. You're right, that would cause us to thrash. We're intelligent in the course of processing the packets to make sure that it is almost always true that by the time we get to doing something, everything we need is in cache. Yes?
I should have clarified. So let's say you do that, but now you're going to the next stage, and let's say it's a homogeneous vector. Everything is going down to the next stage. You are now going to take a cache miss for the first element of the vector because you just went through the whole cache trying to bring in all the data.
Yeah, no, absolutely. So there is a cost going node to node through the system, but it turns out, and again, this is stuff that comes out of 15 years of experimental work on real network traffic. It turns out the statistics actually break better this way than trying to run a circular loop path by an incredibly wide margin. So a lot of this stuff is empirical. If you sit down and you talk to some of the people who've been with this project for 15 years and you ask, why two packets in a loop seems to work better than 4 most of the time, the answer is, fuck if I know, it just does. Cool. Really quickly, it also gives you a very flexible plugin architecture. So any kind of network feature you want to add, and there is no end of network features you want to add, can be done as a plugin that can introduce new graph nodes. It can rewire the graph. You can even use this mechanism for, there we go, for bringing in hardware acceleration where you can basically offload some but not all of the graph nodes to hardware. So there's a lot of flexibility in the system. Sorry, there's a little latency there. So one of the things we're extremely proud of, and we hit this last summer, is that we can actually route a terabit per second of traffic on a commodity server using a minority of the cores in the box with millions of routes in the routing table. And it turns out this is really entirely down to PCI lanes because we're actually not CPU bound at this stage. It really is how fast can you get the packets from the NIC to us. This slide does a breakdown of a lot of interesting things here. One of the ones I'm particularly fond of is someone went through and looked at the average number of instructions per cycle with the new Perley chips. We're averaging 3.28 out of a possible 5. So we're very serious about using every trick available. We're also doing a ton of work on integration. It turns out the whole world is moving to Kubernetes. Everyone is very excited about cloud native. And our ambition is not to simply be some bespoke piece of software that someone with an application they care very, very much about lovingly crafts. We actually want to see all of network I/O move into user space. And with the leap that microservices are doing in Kubernetes, this is not only possible, it's advantageous. Because that entire leap is about getting all of your work abstracted away from the particularities of the kernel and into user space anyway, in a way that you can pick it up and move it however you'd like. VPP fits very, very well in this. There's been a bunch of integration work done, and this is something we'd be very interested in collaborating with the SPDK community on to get SPDK into the same place where you have general deployment user space, storage and networking. So really quickly, going to go through some of the TCP stack stuff. So VPP has its own pure user space, high-performance TCP stack. And what really motivated this was container networking. Because it turns out that as you're scaling up the number of containers you run in a box, and every one of them is coming with an interface, the amount of work that you need your stack to do scales up tremendously. Now, our dear friends here at Intel keep shoving more and more cores at us. We're very happy about this. It means you're going to run more and more pods on a single server. So right now, people are running between a few hundred pods. One could easily foresee a foreseeable future where that's a few thousand pods. When you're expecting relatively good rates of return in terms of the TCP connections per second and the number of TCP connections you can maintain, you really have to rethink how you architect the entire system when you're thinking about supporting millions and millions of simultaneous connections and hundreds of thousands of connections per second. And we've done that work in VPP. The other thing we did was we realized that you need a TCP stack like you need a hole in the head if you have two containers running in the same box. All you really need there is a memory FIFO, and we can cleanly give you that memory FIFO between 2 pods in Kubernetes without you having to worry about it, right? It's just something we can do for you as an offload mechanism. Really, really simple dive into the stack, right? Effectively, what you have is VPP as a user space process. It supplies not just the TCP stack, it supplies the entire L2 and L3 stack, including an intensely rich variety of features. It comes up, it keeps a session layer, it's got a binary API that it exposes to the application. The native binary API simply involves shared memory, receive, and transmit queues. Obviously, for legacy applications, there's work also going on in Fido for producing LD preload gems. But if you care about performance for TCP, you very quickly discover that the Berkeley socket API itself is a bottleneck. And there's a bunch of people with a bunch of interest, not just you guys with storage, people looking at proxies like Envoy for Service Mesh, and a bunch of other places are interested in doing the extra work to get the extra performance with a better API to TCP. So we give that to you in terms of a shared memory, transmit receive queue into VPP from your application. This is, again, standard shared memory. We use, MIMFDs to pass them around. They're in fixed positions and sizes. There's a bunch of different options for the things you can do. You can peek ahead, so you don't necessarily dequeue things, you just look at them. And there's even more space. What I would suggest to you guys is stop and think for a minute what you would want from your host stack if you were no longer bound by the shackles of the Berkeley API. How many folks could think of something interesting that would make your life better if you no longer had to be bound by those shackles? Okay, there are some of you. Find me later, because I'm very interested in having that conversation. So again, we did a clean implementation here. We've actually had to invent entirely new algorithms for dealing with timers, because when you're staring at the wall saying, I'd like to be able to support tens of millions of simultaneous connections, and that means 6 times tens of millions of timers that I have to service, that's a hard problem. And you have to think deeply about how you're going to deal with it in an efficient and effective way and maintain performance at that scale. So this is where SPDK comes in. And you'll hear more about this from Tomek in just a second. So imagine that app simply being the SPDK iSCSI stack. Now, not only do you get TCP here, but we've actually constructed the system so that the transport layers are pluggable. So we've already had somebody implement SCTP. We support UDP. We're currently offering TLS offload. There's work underway to have that TLS offload do hardware offload, so you get the crypto completely off the box. There are people making dark noises about implementing QUIC. How many folks have heard of QUIC? QUIC? Okay, if you haven't heard of QUIC, you've got to go look into QUIC. It's a TCP replacement that you will absolutely want in your life. The other thing, and this is really important, is we bring the very sophisticated feature set that eventually a customer is going to ask for that you don't know anything about. So imagine, for example, a customer who decides that for your iSCSI traffic, they would like to do particular traffic engineering that requires it to use segment routing v6. How many of you even know what I just said? I see 1, 2. 2 of you know what I just said. How many of you want to know what I just said? Okay, you're just curious people. So the truth of the matter is, part of what this enables you to do is when your customer comes to you and says, mumble, mumble, network, mumble, mumble, you can say, there's this lovely documentation at the Fido project that will give you mumble, 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 mumble when you configure it, and you don't have to change anything about what I've done, right? And that's a huge win for you guys. So this is my blue sky slide, right? This is sort of a future thinking way of dealing with this stuff, which is right now you've got an SPDK iSCSI process, you've got a VPP process, they're communicating over shared memory. So we're all relatively trustworthy people here. What if we could use the plugin mechanism that we have in VPP so we could bring the SPDK threads, pegged to whatever cores you need, into the VPP process so that we could actually share memory between us and do smarter things there. So that we could actually collaborate in a closer way without having to keep each other quite at the same arm's length. This is what I talk about as the unified storage networking graph. And my gut is telling me that there are big wins here for both of us. We just need to take some time to explore them. And I apologize, I'm probably hugely over time. I'm going to hand it back to Tomek.
So now you know why the VPP is awesome, and you can see right now how it's integrated in the SPDK at this time. So just to reiterate, that's the architecture that we had before the latest release. With 18.04, the architecture is expanded to allow a possibility of using another set of APIs. In this case, we're using APIs provided by VPP. So it's possible to interact with separate VPP process via shared memory, as noted by Ed. So please note that in this case, there is no kernel in the loop anymore. This new usage model simply relies on user space all the way. So particularly, we are utilizing the VPP communications library, in short VCL, to give that communication over shared memory. So since this brings user space to whole data path, it means that there are no more syscalls throughout, as well as we have a better CPU utilization due to no longer relying on interrupts. So another benefit that Ed very much touched on is the possibility to use the extensive VPP capabilities, networking capabilities, as well as any other integration that is present there. So we're enabling any kind of feature that VPP already has. So going back to the iSCSI abstraction, so we have to keep in mind that iSCSI target was written in such a way to not depend on any particular net framework. So that makes it possible to both use by any kind of library, in this case the one responsible for iSCSI communication, as well as use any kind of APIs available. In this case, we have two kinds, the POSIX sockets that were used previously, as well as VPP API right now. And all of them can be used at the same time, so you can have connections coming from both of them in the same running target. To reiterate, POSIX sockets are still available, they're not going away. If you want, you can still use them. So VPP support is optional. It has to be compiled in to work with SPDK target. So another part that I touch on is that we can use this net framework with any other libraries or targets that we have. So in future, that's probably meaning the NVMe over Fabrics target. Okay, so let's say you've been running iSCSI target or want to start on. Here are a couple of steps to get you started with VPP along with SPDK. As of this release, you can actually perform all those steps. So basically, first that you have to remember, compile it in as it's optional. Then you run the VPP process to configure any service that you want, and in particular the interfaces that you would like to use with SPDK. After such configuration is complete, the iSCSI target can be started and will be the interfaces that you've configured will be available in the iSCSI target. This and a lot more is available on spdk.io in iSCSI target documentation. There are links present for VPP to guide you through any of the VPP CTL utility configuration. So this question probably comes up. You might be wondering, what about the performance data? Well, all of this, the VPP integration, is a new development that was added in 1804. SPDK is a rapidly growing project, and we wanted to bring everyone to the forefront of the changes, thus this presentation. we are currently gathering numbers and of different usages to provide enough data points to actually give you the answers. But you can get started using it right now by just downloading our latest release. So that's it what we had with Ed for this presentation. If you have any questions either to me or Ed, please go ahead.
Okay. Yeah, there's a lot of content, in this talk. Is you guys going too fast? So I'm new to this VPP. Can I ask a fundamental question? So the VPP, you talk about the instruction cache, data cache. Are you there's a dependency? Do you rely on some like Intel IOAT when the packet come in? So the header going to the instruction cache, data cache? Then you're processing that?
I didn't quite, do we rely on the Intel what? There was a word I missed.
The IOAT type of thing, so the packet come in, instead of the whole packet go to the memory, so the header go to the cache, so you can do the vector processing?
It's called CBDMA.
Oh, okay. Yeah, I don't think we're currently taking advantage of that. That would be certainly be something interesting to start taking advantage of going forward, because being able to load directly in a cache would be of interest. There's an interesting question there, and it gets back to the question that was being asked about the cache impacts on the data cache side. Again, about the trade-offs of the vectorness of packets versus the iCache hits on the particular nodes. So that would be an interesting thing to explore, but I don't think we've currently explored that.
Yeah, but I don't really understand though. When you talk about iCache, data cache, instruction cache data, what are that about? I mean, so you still the packet is still going to the main memory. Then you fetch the header into the the CPU, the iCache, Dcache, then you do the vector processing. That's like a workflow when you do.
Yeah, typically as we're chewing through a vector, we're doing the prefetch while we're processing a set of packets already. And so typically by the time we get around to processing the set of packets we sent the prefetch for, they're already present. One of the things that we've actually found historically over time is there are always a new set of sophisticated things you can do, and you have to go out experimentally and determine whether the thing that sounds like a good idea is actually going to produce performance. Because it doesn't always. There have been a ton of experiments that we've done with much more complicated algorithms for scheduling packets. We've done a bunch of experimentations on how pipelines are structured. We found some places where advanced features like the AVX instructions buy us a ton of stuff. We found some places where it turns out the additional complexity doesn't. And so that set of instructions in the Intel chip may prove to be fruitful or may not, but you can't really tell till you actually dig into using them.
Okay, so why this has to do with the user space? I mean, assuming you understand what you talk about, but why the VPP is the user space, TCP?
VPP is user space, just like SPDK, yes.
So you depend on DPDK to make it user space? I mean,
no,
all the things you talk about is still in the kernel, right?
So if you are using a physical NIC that is supported by DPDK, we will use the DPDK drivers to haul those packets into user space.
Yeah.
There are lots of other sorts of things where you end up hauling packets in other places. So I'll give you one example that's concrete. If I have two containers running on the same box that need to talk to each other, and they need to pass packets back and forth between each other, it turns out the fastest thing you can do is we've got something called MEMIF. It's a highly optimized pure memory interface between them. That interface mechanism ends up being basically the fastest way to move packets between two processes running either in containers or not on the same box, right? So we do use DPDK where it does really good work schlepping things in from NICs to threads on cores, and then in other places we don't. The actual packet processing bits do not use any DPDK code. In fact, DPDK is built as a plugin for VPP. The DPDK input nodes are built as plugins because we have use cases where you don't want them. I'll give you a really good example. We have a lot of people who are doing instructional material where they will stand up a bunch of VPP instances on a box and get them all linked together with memory interfaces in order to teach networking, right? When you do that kind of a thing, it turns out trying to stand up a bunch of different instances of DPDK on a box has some interesting tricks that are more complicated than most people want to deal with. So there are places where it actually does really, really good work where we use it, but it's certainly not something we depend on in a strict dependency sense.
Okay.
Yes? Can we get a mic to you?
Hold on 1 second.
Oh, here we go.
Out-of-order packets, how does that work in VPP? And also, can you use multiple also, can you use multiple cores? And you know, how do you?
Oh, we absolutely use multiple cores. We basically have embarrassing parallelism. So we'll use RSS to spray packets across multiple cores. And then because we're processing them as a vector, as they pass through the graph, we literally do sort of a, with some modifications for the heterogeneous vector case, it becomes a run to completion. So you can see very simply in the run to completion case, your packet ordering ends up being sort of preserved there as it's passing through that core. The embarrassing parallelism, because we're using RSS to spray across them, and we literally just keep a copy of the graph running on every core, means that you're rarely passing packets between cores. And so as a result, you get almost linear scaling as you ramp up the number of cores. And again, there's some funny nonlinearities that you run into where you will get up to a point where we're fully utilizing the cores, but if you keep throwing more packets at us, we continue to scale well because of the amortization effects. And what we see primarily is when you hit the magic number of cores, those cores aren't completely consumed, but you're running out of PCI lanes. So, more PCI lanes. We like PCI lanes. Yes?
I have a question. One of the differences that you might see with you trying to do your technology with SPDK is that you talk about prefetching the data packets. Mm-hmm. For SPDK, we discovered that you also have to worry about prefetching the on the completion queues and the submission queues as well that are not the actual data itself. And does that present any challenges to your prefetching architecture?
That sort of comes down to, I think the way that the analogy here is very likely, because you've basically got queues of control messages and then queues of actual blocks, right? That's what you're describing. And so the analogous thing for us would be prefetching just enough to get the header information we need, as opposed to prefetching the entire packet. Because for most of the processing you're doing, you don't actually need the entire packet. You just need however many bytes to get deep enough into the header. Make sense?
Okay, it's not quite a perfect analogy in the.
It isn't perfect by any means. I agree.
Because the one other thing we found with prefetching on completion and submission queues is the time when I actually have to do the prefetch is very strange. Like for example, for completion queues, I'm actually trying to prefetch it at a time when I'm kind of halfway when the hardware is kind of going through its ring and it's halfway through the ring. That's when I want to do my prefetch based upon some other completion. It's not at the time I'm trying to process the actual completion queue message
That is actually tremendously fascinating to me if you could find me afterwards, because part of the thing I'm really interested in doing is, as I said, I'm a networking guy, which gives me just enough information to believe that I know something about storage. Clearly I don't, and I'm very interested in understanding more about that particular problem. Okay. Yes?
One question is, why is VPP a separate library? Is it not, why is separate process? Is it not available as a library which can be compiled with the rest of the SPDK?
So there are a couple of things there. One is that we function best. Well, first of all, the reality of the situation is that people who run virtual switches and virtual routers actually want to process, right? And you can do basically anything except resizing the heap simply by putting a plugin into VPP. So if you actually want to do something different in terms of packet processing, you can have an entirely independent source tree. You can build your plugin, you can drop it into the plugin directory, and it will load on startup. And you can do whatever you need to do in terms of rearranging the graph. And so it actually makes sense to not reinvent all the initialization logic, all the other pieces involved and whatnot. And so it makes sense as a process as opposed to as a library as a general rule. The other thing is that obviously, for the same reasons you guys run into, you're very particular about owning cores. We can function perfectly well without core CPU pinning. And it's typically faster than anything else you would do that doesn't do CPU pinning, but it's a shadow of the performance that you get with CPU pinning. Other questions? Do we have questions for Tomek? He actually did some really cool work.
One of the slides you showed that NVMe OF integration with VPP.
Yeah.
So is it a compile time also, like iSCSI?
He's asking about NVMe over Fabric. That's clearly you.
Yeah. So you're asking about this part where we're working with NVMF, right? Yeah. Oh, exactly. Yeah, that's the point. Anything over the net framework is completely separate from what's in the bottom. So in the future, basically the NVMF target will be allowed to use anything that's available up here when the changes for TCPIP are done in the NVMF target. Yep.
Okay, so we got one question over here, and I'm just going to point out, I don't mean to question shame anybody, but the left side of the room is beating the right side. So you guys got to
I'll question shame the right side.
Okay, here I will help out with that. So do you have any like performance comparison with VPP versus kernel TCP/IP stack? Do you have any charts, numbers?
VPP versus what?
It's coming up. VPP versus the other TCP/IP packet processing mechanism, like whatever is default comes in
so
the
we're,
system.
we're actually in the process of standing up increased TCP testing in our continuous performance lab. So we actually take a continuous integration attitude towards performance with VPP. So we literally have a bunch of equipment sitting in a lab that we go ahead and run a standard set of open source testing against that gets run. We're almost to the point of being able to run patch by patch as patches comes into the CI system. We've had a variety of people who have gone off into their corner and run benchmarks, but that doesn't give you the same kind of standardization that we usually want to stand behind in public for these things that you get out of that open benchmarking process. One of the things that we've discovered is open benchmarking is actually hypercritical to playing in this space in a credible way. And that's why we invest a lot of time and effort in doing that.
So you don't have any graphs or numbers to share this time?
Not at this time, no, because again, the CI is getting stood up. We're literally in the process of bringing up a bunch of new hardware up in our continuous performance lab so we can support that level of testing.
Okay, thanks.
Cool.
Any other questions? Awesome. Thank you, guys.
Thanks.